When we study history, we naturally put humanity at the center of the timeline. We measure epochs in centuries and millennia, creating a comfortable illusion that our existence is the main event of reality. To see how skewed that perspective really is, we can use a framework popularized by astronomer Carl Sagan. He called it the cosmic calendar, a model that takes the entire 13.8 billion year lifespan of the universe and compresses it down into a single 365-day year. At this highly compressed scale, every single second that ticks by represents roughly 438 actual years of real time. The Big Bang kicks off at midnight, January 1st, but our Milky Way galaxy doesn't even form until early March. For the vast majority of cosmic history, our local neighborhood did not exist. The universe spent over 8 billion years evolving, entirely indifferent to the fact that we would eventually arrive. We have to fast forward all the way to late summer to find our origins. The solar system, including Earth, finally condenses from a cosmic nebula in early September. Life begins as simple cells shortly after, but complex multicellular organisms don't appear until December 5th. Dinosaurs arrive late to the party, dominating the Earth right around Christmas. Their reign ends abruptly with an asteroid strike on December 30th. That sudden ecological reset is what finally clears the way for mammals to spread and diversify. So where do we fit in? Anatomically modern humans do not step onto the stage until 11:52 p.m. on December 31st. We have existed for exactly 8 minutes of the cosmic year. All of recorded human history, beginning with the invention of written language, occupies only the final few ticking seconds before midnight. And the modern technological era, from the Industrial Revolution to the digital age, fits into the last few milliseconds of the final day. If our entire existence is a fleeting spark in cosmic time, our physical footprint must be equally microscopic when compared to the volume of the universe. To understand our spatial footprint, we have to look at the observable universe. This is a region of space defined entirely by a universal physical speed limit, the speed of light. This animation shows our observable bubble. You might expect a 13.8 billion-year-old universe to be 27.6 billion light-years across. But because the fabric of space itself has been expanding the entire time light has been traveling toward us, our observable sphere is actually about 93 billion light-years in diameter. That hard edge is called the particle horizon. It is the absolute maximum distance from which a photon of light has had enough time to reach Earth since the Big Bang. The particle horizon is an optical limit, not a physical wall. There is no edge to bump into. The cosmos continues past it, leaving us to figure out how to mathematically comprehend a volume of space that large. This is an old problem. In ancient Greece, the mathematician Archimedes attempted to calculate the volume of the cosmos by estimating how many grains of sand it would take to fill it. To do this, he had to invent entirely new mathematics utilizing large exponents. Ultimately, he estimated it would take 10 to the 63rd power grains of sand to pack his ancient 2-light-year-wide model of the universe. This data visualization illustrates the leap from Archimedes' math to modern astrophysics. To fill our actual 93 billion light-year observable bubble, you would need roughly 10 to the 95th power grains of sand. This calculation encounters a wall. We are only measuring the space we can see. If the particle horizon is just a visual boundary, the actual volume of the universe likely extends beyond our ability to count it. This brings us to the ultimate cosmological mystery. If we cannot see past the optical boundary of the particle horizon, how can scientists mathematically prove what exists out there? The answer lies in the cosmic microwave background, or CMB. This is the primordial afterglow of the Big Bang, a faint radiation blanketing the sky that carries the geometric fingerprint of the early universe. To read that fingerprint, the European Space Agency launched the Planck mission, a highly sensitive observatory designed to map the CMB and measure the total density of the universe. Density determines spacetime's shape. If there is enough mass, gravity forces space to curve in on itself like a closed sphere. If there is too little, it flares outward like an open saddle. If balanced perfectly, it forms a flat 3D grid. By precisely measuring the geometric curvature of our local observable bubble, cosmologists can extrapolate the shape and ultimately the scale of the unobservable universe beyond. The results from the Planck mission resolved the question. The universe's density balances on a razor's edge. Space is geometrically flat, verified to within a 0.4% margin of error. Because a flat universe lacks the positive curvature required to close back in on itself, it has no boundaries. Assuming it is simply connected, a flat universe must extend infinitely in all directions. The space beyond our horizon continues as a physical reality. Searches for topological loops have turned up nothing. No evidence of a cosmic hall of mirrors where light wraps around to show us duplicate galaxies. We arrive in the final moments of December 31st on the cosmic calendar, assuming our local experience is the center of the story. But the math tells us otherwise. Every achievement, war, and discovery crammed into the final seconds of a cosmic year is playing out on a perfectly flat stage, with no edge, no boundary, and no end.